Okay, my friends, today we are going to cover two things about phase change and all that kind of good stuff. The first thing we're going to do is we're going to talk about temperature and how we measure it. First, we're going to find out, I'm going to specifically define what temperature is, because last time we talked about specific heat, which linked temperature and energy, and we kind of put energy in a box and defined it as the ability to do work. And we are going to look at two types of energy, kinetic energy and potential energy. And we talked about how specific heat linked that energy and temperature. So today we're going to define temperature. We're going to nail it down so we have that idea wrapped up. We're going to look at how we measure it. There are actually two ways that science likes to measure temperature. And then we're going to talk about the three phases of matter. We're going to dig in a little bit deeper so that we look at what the difference is between the three phases of matter in terms of particle behavior. Particles being, atoms and molecules and stuff like that. So let's get going. Let's get some knowledge like this with temperature. So temperature is the measure of the average kinetic energy. That's what it is. Kinetic energy is the energy of motion, and temperature is the average motion of molecules. Really, it tells us how fast those molecules and atoms and particles and stuff are moving. So if something has a low temperature, that means that those particles are moving around kind of slow. A higher temperature means that they're moving around with a lot more speed. It's almost like a speedometer. Thermometer is like a speedometer for atoms, sort of, in a weird way. That just melted my brain. Anyway, this is what you need to remember, or at least have memorized, is temperature is the measure of the average kinetic energy. Got it? That's what you need to know. So, how do we measure it? Well, first of all, let's talk about Celsius and Fahrenheit. Back in I think it was the 1700s, I could be wrong, ask Wikipedia or something like that. I think it was in the 1700s when when they were making thermometers. Lord Fahrenheit based his scale on the human body, and Lord Celsius based his thermometer on water. So basically, back then, a thermometer was pretty hard to make. You needed some highfalutin lab stuff, and so it's kind of like, you guys are probably all too young to remember the battle between VHS and Betamax. Well, maybe it's sort of the same thing between the battle between I don't know, Apple and Android. It's just two different ways of doing things, and it turns out that Celsius is the one that the almost the entire world went with, because it was really, really easy to calibrate these thermometers, right? Because Celsius is based on water, right? So everybody has water. And all you had to do if you got a Celsius thermometer is you boiled some water, put a little mark on it, that's 100. And then you plunked it into some ice water and put a little mark on it, and that was 0. And there's 100 spots in between, right? So it was really easy to calibrate, really easy to understand. And so Celsius kind of took over everywhere except here. Because I don't know why. Anyway, so Celsius is the temperature that almost everybody measures temperature with. And because almost everybody uses it to measure temperature, that is what science adopted, because that's what everybody was using, was Celsius. However, there was a problem with Celsius, right? So look at this right here. Celsius says that 0 degrees is the freezing point of water. Now, I know for a fact that every single one of us is aware of the fact that it can get much colder than 0 degrees Celsius. That's freezing. That's 32 degrees Fahrenheit. So we know that there is a temperature below 0 Celsius, which kind of doesn't make sense, because if you're measuring the average kinetic energy, you can't have negative temperature. You can't have negative kinetic energy. You can't have negative movement. So it just doesn't make sense. And if you're measuring temperature and you can go below 0, why? It doesn't make sense. Shouldn't 0 be where there's no energy, where there that's 0 should be at the bottom, where there is no kinetic energy. And that's kind of what happened in science. People were having this problem because 0 wasn't actually 0. the 0 Celsius didn't actually measure 0 temperature. Very much of a big problem, especially if you try to math with 0. You put that 0 right there, you put that 0 into a calculation, and all of a sudden your calculations don't work anymore because you can't divide by 0, which is, it didn't work, right? So along came this guy. His name is Lord Kelvin, and he changed it. He kind of like came up with like a new scale, and his scale is called, believe it or not, it's called the Kelvin scale. The Kelvin, named after Lord Kelvin. Now, like, all he did, all right, so before you copy that stuff down, what he did is he put the 0 Kelvin at 0, right? So he said that his scale, like he basically took like a Celsius thermometer and just erased the numbers. So now it had the same like hash marks, the same like degrees of Celsius, but instead he put 0 at what he defined as absolute 0, where it's actually no kinetic energy. And so this is a pretty important thing to like keep in mind, is that because he basically started with a Celsius thermometer, and 1 degree Celsius is that big, 1 Kelvin is also that big. So if you look over here at these thermometers, like this difference is 25 Kelvin, right? And this difference right here, this is 25 Celsius, right? This is 12 Celsius, and this is 12 Kelvin, right? So a change in temperature of 12 degrees Celsius is exactly equal to a change in temperature of 12 kelvins. And he did that on purpose because all of the equations and all the mathing that had been done for like hundreds of years so far, it was all based on Celsius. So he was like, man, let's not redo every single equation, and let's just instead just like erase these numbers and start anew. And so he like sort of came up with this idea of 0 being at the bottom where there is no kinetic energy, and he dubbed it, he named that absolute 0, right? Because we know that it gets colder than freezing outside. My goodness, when was the last time you went ice fishing and it was below 0? Yeah, it gets a lot colder than 0 out there, right? So 0 Celsius is very inaccurate. It's not 0 average kinetic energy. So we just take that 0 and you push it down to this new thing called absolute 0, and you've got the Kelvin scale. And it turns out that you have to drop the 0 by just about 273 degrees. Got it? And when you do that, you hit absolute 0, which, let's define it. Absolute 0 is the lowest possible temperature. It's where all the particles stop moving. There is 0 thermal energy. Okay? You guys picking up what I'm putting down there? Now, absolute 0, man, that is some trippy stuff right there. Absolute 0 is weird. It is very strange. It is a very strange, really weird things happen to matter when you start hitting absolute 0. But for us, we just need to know that it's the 0 point for the Kelvin scale, and it is the point where there is actually 0 average kinetic energy, where there is 0 thermal energy. It is the coldest possible temperature. You got it? And then it's a quick, easy conversion from Celsius to Kelvin, from Kelvin to Celsius. It's just the equation is like right here. And if you forget, the equation is on the back of your reference table. It's quite delightful. So if you had 362 Celsius and you needed to convert it to Kelvin, well, here is your equation. Kelvin is equal to Celsius plus 273. Right? So you put 362 here plus 273, and that will give us, let me do some math. Nice. All right. So it will be 635 kelvins, and we don't say degree kelvins, we just say kelvins, because degree Celsius is silly. Like, why do we say degrees? It was a kind of a mistake. We should never be doing that, because we don't say, well, how far is it from here to there? It's like 10 degree miles. That makes no sense. How much do you weigh? I weigh 72 kilograms. Yeah. So the unit of measurement is just Kelvin, not degrees Kelvin, just flat out kelvins. Yeah. Sweet. Oh, now that's crazy. Here we have 896 kelvins. Well, that's equal to Celsius plus 273. So to find Celsius, we subtract 273 from both sides. It's just that difficult. Or not. But that's it for temperature, guys. Like, that's the most we need to know about temperature. We need to know what it is and how we measure it. And we will be measuring it with the Kelvin scale because that's what all science uses. And again, science uses Kelvin because the 0 point of Kelvin is actually at 0, like kinetic energy, because temperature is the measure of average kinetic energy. Lovely. So let's talk about our 3 phases now. That's the second half of what we need to do today. So we have solid, we have liquid, we have gas. So solid, the volume is definite. We know exactly what the volume is, the same with the shape. In other words, it doesn't change. Now for a liquid, the volume stays constant, but the shape can be whatever it wants, which is awesome. That's how we get hydraulics. You got it? So, well, actually, we're going to talk about that in a little bit. Now, a gas, on the other hand, the volume is not set. You can expand and contract and squeeze a gas. It can go big and go small. You can compress. You can expand. It's all over the place. Same thing with shape. It takes the shape of whatever container you happen to put it in. Does that make sense? That's the easy stuff that you should already know. But what I want us to learn or like dig into is this thing. It's called the kinetic molecular theory, and it states that all matter is made up of particles in constant motion. And now let's come back to this word one more time again, because this is a thing. It's a thing where people are like, oh, it's just a theory, dude. A theory in a scientific context is an explanation based on scientific fact. It is an explanation, right? We use the word theory in science because we're always open to going back and revising it once we learn more information or once we learn something new. So a theory is an explanation based on fact. It's not a guess. That's a hypothesis. So please don't get those mixed up like everybody else in the world. So kinetic molecular theory states that all particles are in constant motion, which is kind of weird if you think about it, because a solid seems to be like, not going anywhere. It doesn't seem to be just sort of moving around, but the particles are in fact moving, right? So the difference between a solid and a liquid and a gas, if you notice, is the distance between the particles. A gas has a very big distance, liquids have very much smaller distance, and solids have as little a distance as possible. Right? You understand what I'm saying? But it doesn't matter. They are still moving. Even when something is solid, they are still kind of like doing this, like vibrating back and forth, jostling around, but they are in a fixed position. In other words, this particle right here is not going to be bouncing all throughout the sample. Whereas a liquid, they are still vibrating and jostling around and jiggling and bouncing and hitting each other, but in a liquid, they can move around. So this dude right here can end up anywhere along the sample. The difference is in a liquid, they're still stuck together, right? They're still kind of held together, so they can't quite break apart. Now a gas, definitely moving around like all over the place, but they are moving so violently, so strongly that they are able to break away from one another, and they go wherever the heck they want. They fill the entire container, right? So what that means is the more temperature we have, right? Because remember, temperature is a measure of the average kinetic energy, the energy of motion. That means more motion. It means, so the higher temperature means there is more motion. They're moving faster. Does that make sense? So the intermolecular force, so this is something to keep in mind, is the intermolecular force of attraction depend on distance. It's just like magnets on your fridge. You get them close, they stick really strong. You pull them really far away, and it's like they don't even, like there's nothing. Like the force is basically gone. Does that make sense? So the farther particles get, the less intermolecular force of attraction you have. So in a solid, they are very, very close, right? That means you have the highest amount of intermolecular force of attraction. It's not in the notes. You should probably write this down because it's really important to know. Now, a liquid, they're going to have like medium intermolecular force of attraction because they're sort of like, they bridge the gap between right next to each other and really far apart. So they have like a medium amount of intermolecular force of attraction, whereas a gas, these things are so far apart, there are almost no intermolecular forces of attraction. And so basically what we're doing is as we heat a sample up and add kinetic energy, the particles are actually breaking further and further apart. Got it? Awesome. Now a solid, like I said, larger than the intermolecular forces of attraction are larger. It's like the most. No, not the most. The most. Right? So that is where you will find the most intermolecular force of attraction. So the particles are held fixed. In other words, they don't move from place to place. But they're still vibrating and buzzing around. And this is where you often get regular geometric arrangement of your atoms and molecules. Got it? Very close together, still vibrating. Liquids have medium intermolecular force of attraction. Now they're still being held together pretty good, but it's kind of easy to break them apart. Like, just take a glass of water, pour some out. There, you just like broke the intermolecular force of attraction of a liquid. It's not that hard to break them up. But the water molecules are still being held together, right? Because they're still water. So in a liquid, the intermolecular force of attraction are medium. They're still holding on, right? They're still holding on, but not terrible strong. And because they're not holding terrible strong, the particles can move from place to place, but they still can't separate, right? They can't quite break free from one another. So what happens is the particles roll and slide, oddly enough, in a liquidy kind of motion. And so when you pour, gravity pulls particles downhill. So when you pour water out of one thing into another, the reason why it lands on the bottom of your glass and sort of fills the bottom of that container is because gravity's pulling it down that way, right? So if you were in space, the liquid just sort of bloop into a ball and just sort of like float around because there's no gravity to bloop them into the bottom of the container. And last but not least, gases. This is where the intermolecular force of attraction are the least, or like the lowest, compared to solid and a liquid. And in this one, in a gas, the particles move, and this is important to know, independently. In other words, like, they are so far apart, they have almost no interaction with one another. They don't stick together. They don't, like, nothing happens. And because they are so far apart. Now, when I say far apart, I mean compared to the size of an atom. So compared to the size of the atom, they are very, 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 very far apart. I mean, close enough. I mean, air is there. We can feel, when a gas is there, we can feel the wind in our face and stuff. So, I mean, the particles are there. They're like, for me and you, we would consider them to be like pretty close. But on an atomic scale, they're actually pretty far apart. And because they're so far apart, there's no intermolecular force of attraction really whatsoever. At least we pretend like there isn't. And then these particles spread to fill the entire container. And the thing is, like with the gas particles, because they're so far apart, right, they have this huge distance between them. And what that means is that distance, we can like compress them. We can like bring these things closer together, right? So here we have like 6 particles. If we wanted to, we could take those 6 particles and we could put them in a box. Oops, and we could compress them. And what that does is it takes the distance between each particle and it greatly reduces the distance, right? So they are much, much closer together. And gases are the only phase where you can do that. It is the only phase that can be compressed, which is why if you guys are going to start driving, like all y'all are starting to drive soon, this is super important to know that liquids cannot be compressed, at least not enough for us to care about, but gases can. So look, here's the deal. See this? This is how your brakes work, and you all need to know this, especially if you're driving around in the North Country with all the salt on the roads and stuff. So this is how your brakes work. This is your gas pedal. Just pretend there's a little pedal there. And what you do is when you press on the brakes, you press this thing called the master cylinder, and it squeezes a fluid all through some tubes that go wiggling and winding all over from your engine compartment down underneath, and like it crisscrosses and goes to all 4 tires, right? So it breaks out into all 4 tires, these little tubes, and then it comes into here, into these parts called your calipers. And your calipers have these little hydraulic tubes, and what happens is, as this hydraulic fluid is pushed this way, the calipers squeeze together, as you see down here, and it grips this thing, right? Ooh, that thing right there, which is your discs on your tires, and that's what slows like your wheels from spinning, and then eventually stops your car. It all works really well. Even like the daintiest little push can produce a lot of power. However, the problem is if air gets in there. Now this is what happens if air gets in your brakes. See, if there's air, what happens is as you squeeze or step down, instead of having this where all that force is transferred, instead of lifting this like by going in to squeeze your brakes, the gas gets squished. See, do you see how that air bubble is getting squished? And so when you're driving your car, if you have an air bubble in your gas line, you go to step on the brakes and you just kind of go like all the way down to the bottom, because you have something like, wait for it, like that. You have a little bubble of air in your line. Ain't nothing good about that. You know what I mean? Because that means that all the pressure is going to squeezing the air bubble and not going to here to squeeze your brakes. So here's what you do. Here's what you do. Everybody who drives anywhere needs to know this, is if you do get a bubble, and let's say there's a little bubble in your brake lines, and you're stepping on the gas and nothing's happening. You see what this lady is doing? She is pressing and then releasing and pressing and releasing, pressing and releasing. But that is exactly what you do, because what happens is you have a big reservoir of brake fluid up here. And so you squeeze it, and then you let go and you squeeze it again, and then brake fluid will come out of the reservoir and fill this until that gas bubble gets squished, until it is almost like completely squished, and then the force from the brake can be delivered to your calipers. So anytime your brakes get squishy, it's because you have the wrong phase in your brake lines. It must be all liquid, because hydraulics work with hydraulic fluid, not hydraulic gases. There's no such thing as hydraulic gases. That makes no sense whatsoever. So there's your daily tip of survival for the day. Man, squishy brakes mean you keep pumping them, and if that happens, you go tell someone so they can bleed your lines and get all the gas out of there. Because you do not want gas in your brake lines. And that is it for today. The worksheet for this one is phases of matter. It's going to be the multiple choice one. And yeah, I think that's it, guys. I hope you have a super duper awesome day. I know I am going to, and I will, as always, see you very soon.